Okay, so this first question up here, I want give me a couple of examples of something that would be considered a heterogeneous mixture.
Sand and water.
Sand mixed with water?
Yeah.
Okay.
Pizza.
Sand plus water, or pizza. I like that. So this hetero, what does this thing here mean?
Different.
Different. Okay. Now examples of the homogeneous.
Milk.
Hopefully, yes. Milk would be bad if it wasn't.
Aluminum foil.
Milk. Aluminum foil. That's semi-subjective.
What about sugar?
No, that's a pure substance.
I think that was on the test.
Sugar and water mixed together?
Sugar and water mixed, sure. What?
Wasn't that on the test the same all the way through? Was it aluminum foil?
Yeah, it's supposed to be the same. It doesn't change the color.
Right.
Genius, whatever in the book it says.
It's got to look the same all the way through.
Yeah, they gotta look all through this.
But if it looks all the way through, does that, if you're looking at a substance and it's the same all the way through, does that immediately mean it's a homogeneous mixture?
No.
No, because what else could it be?
Because it could be like sand or
It could be a,
Say it, go ahead. You got it.
I know, I just lost it.
It could be a pure substance, or it could be an element or a compound, or a compound.
I was thinking of the substance.
So when we're looking at sugar, and sugar looks the same throughout, why does it look the same throughout? Not because it's a homogeneous mixture, but because why?
pure substance.
Because it's a pure substance, so it has to look the same throughout. Okay, sugar and water, that's, yeah, sugar, like sugar water, for sure. If you take like a tablespoon of sugar and dissolve it in some water, that's definitely a mixture, and that's gonna be homogeneous, for sure. Why is that doing that? All right, so differences between chemical change and physical change. What's the major difference? What? Composition. It's about a composition change.
And then a chemical change changes the composition.
So a composition change happens in a chemical reaction, right? And it doesn't happen in a physical reaction. So the physical changes are pretty simple, and we usually classify those as what? What constitutes a physical change?
Right? State.
Change in state, like going from a liquid to a solid, or a gas to a solid. Any kind of phase change is going to be the easiest way to talk about what happens during a physical change. So what we have here is a chemical change, and that chemical change is really talking about the formula.
Yeah, the matter type, the change in the matter's composition.
Yeah, and to have an actual change, we're going to be talking about the fact that it went from, say, the easiest one would be, or an easy one would be H2O2 turns into oxygen and water. So the substances on each side of the arrow, they're not the same. So that's definitely a chemical change. All right, so what are the three things that you observe that will let you know that you probably just saw a chemical change? Okay, so I have a color change, like a piece of wood going from wood color to blackened, or what else? Bubbles.
State.
So if you were to take vinegar and drop it on like a seashell and wait, you'd eventually see bubbles there, and those bubbles are carbon dioxide being formed, so a new substance is being created. And we're not talking about bubbles that get generated when I take water and put it on a stove and boil the water, because I added heat to it. This is just two things mixed together, and all of a sudden bubbles appear. It might be very, very rapid, or it might be very, very slow. And And what was the last one?
Solids or pure liquid.
GT2.
Right. Precipitate. There's an E right there. Precipitate formed. Okay, so I mixed two clear liquids together, and all of a sudden there's a solid form. So that's the precipitate. Choose a problem. Explain how you would solve the problem using the scientific method. Okay. Somebody have a problem for me? Yeah.
Mine was car trouble.
I love it. I mean, I don't, but I get
And
it.
so first there was an observation that the car would start,
Okay.
but the lights come on.
Okay. So one is what, lights go out, or car won't start. Let's go with that. Car won't start. And then so my problem is that I'm having car trouble. You observe this won't start. So then what are you gonna do?
Well, my hypothesis would be that I'm out of gas because the lights are on.
Okay. Is there anything? Could you do some
Research.
research about that, maybe?
Well, like, yeah, I guess I would test it first, try to, you know.
So let's say it's something a little bit more complicated, like,
You might find a problem on the internet and see if other people have had those problems.
yeah, so mine is, I have this light that came on the dash, and it was like, not a light, but it said B12, and I thought that's what it was. And so then I researched it, and it turns out it's not B12, it's B12, and each of those, the B, the 1, and the 2 mean something different. And it was mostly silly. It was like rotate my tires, and it's time to change the oil kind of deal. But I didn't know what that was until I did the research. So if the car doesn't start, then maybe you can research why that particular thing is happening, and then you can use the hypothesis, like maybe I'm out of gas, and then you can put gas in it, right?
Yeah, test it.
And then 5, did it work or not? And if it didn't work, then maybe you need to go back and do more research, come up with a different hypothesis, and then test that. The one I was thinking about was when I was a kid, my mom decided to make a cake, a cookie-sized cake. They didn't have that kind of thing then, and so she used the regular Toll House recipe, and it didn't work. Like the middle part didn't get cooked and the outside got burnt, so she kept having to change the recipe. I must have ate like 40 pounds of partially good cookie cakes until she finally came up with a recipe. So she had to modify all the different amounts of baking soda and sugar and chocolate and all of that stuff kind of finally worked out for her, and it was like more cakey than cookie, but at least it cooked all the way through, and it was still kind of cookie-like. But I mean, it took her a very long time, so she did some research on it and then just started testing and testing and testing. In her case, the testing part turned out to be the really long one. But yeah, you could use it for pretty much anything. So how about a definition for a unit? What do we got?
Standard form of measurement.
Standard form of measurement. All right.
I added it gives a number meaning.
Okay. It's something that gives a measurement meaning.
Yeah.
How about that? So this standard part, what does that mean?
Used across the board.
Everybody agrees that that's what it is. It is used across the board because we all agree that a foot is this long. That it's not this long and it's not this long, it's this long. And then obviously the other part is we're going to measure something. Why was the metric system developed?
To make measuring uniform.
Uniform? Okay. So
So every region is the same.
so we all agree that a meter is a meter. We all have the same distance units and time units and problem. What does anybody know of any instance where the fact that Americans still use the English system and the rest of the world uses the metric system? How that's gotten? There was a big mishap that happened because of that. It was many millions of dollars wasted because somebody made a calculation in the English system and somebody thought the calculation was done in the metric system. No. We lost a probe to Mars because somebody did a calculation in the English system, and then when the scientists in France were looking at the calculations, they assumed that the calculation was done in meters per second instead of miles per hour. And so this thing hit Mars at like 400 miles an hour when it was supposed to hit Mars at 40 miles an hour. So we kind of lost a multi-million-dollar space probe because of a unit snafu. And we already talked about it, but what's this based on?
Powers of 10.
The number 10, powers of 10. 10 to some exponent, right? All right, so we want to convert this into decimal format. Why is that a lowercase? That seems strange. So I'm going to take this and make it 235800. Okay. Do I put a decimal place right there?
If you want in decimal format,
No. Why am I not allowed to put a decimal place right there?
because it changes the zero.
It changes the sig figs. How many sig figs do I have in my question? 4. So how many do I get in my answer? 4. So if I put a decimal place after that, what happens? It changes it to 6, which we definitely don't want. Okay. Next one. So we'll do 6.5895 times 10 to the what? 4. Okay, good. So that was 4 spots. 1 to get right there. So we're going to convert this guy into scientific note or decimal format. So it's going to be 0.05894. All right, good. And you know to move to the left because the exponent is a negative sign on the 10. And we're going to put this guy in scientific notation. So I've got 9.23 times 10 to the negative 4. That looks good. Okay. All right, so we're going to convert these from inches into meters. We didn't really get into this other than just briefly talked about it, and I'm curious to see your homeworks when you turn them in as to how you did this. But this is the format that we'll be talking about today. So I would do 285 inches, and then I know that for every 1 inch, there are 2.54 centimeters, and that there are 100 centimeters in 1 meter. And then if I do that, I get the centimeters to cancel out. Let me switch colors. My centimeter unit cancels out with this one, and my inch unit cancels out with this one. And so then I end up with 285 times 0.25 divided by 100. Does anybody have that? 7.239 meters. Is everybody okay with that number? You sure? What's wrong with the number as written?
Should it be rounded up?
3 sig figs, right? We only have 3 sig figs here in the 285, so I can't have all of these numbers here. So I'm going to end up needing to do 9, turn that into a 4. You okay with that? So my actual answer with correct significant figures is going to be 7.24 meters. Okay. And then our last one here, we've got convert 2.54 meters per second into miles per hour. Okay, so 24.5 meters, oh no, not meters, feet per second. Doesn't matter which one I convert first, so I'm going to convert the seconds into hours. And so I've got for every 60 seconds, I have 1 minute. And then for every 60 minutes, I have 1 hour. So when I do that, I get my second unit to cancel with my second unit, and an inch unit to, or minute unit to cancel with a minute unit. And then there's my hour unit right there. And so I need my answer to have 2 pieces, hours and miles, and I've got the hour portion. Okay. And so now I'm going to convert that over. I need to get rid of the feet thing. So I'm going to put feet down here. I'm going to put miles up here, and it's 1 mile, and it's 5,280 feet. And then when I do that, then I can get my feet unit here to cancel out with my foot unit there. And now I've got miles. And so the two units that I was looking for, I have now. I've got my mile unit and I've got my hour unit. And so then my answer here is going to be miles, miles per hour. And so then I just need to do the calculation. Does somebody have the number for that? 60.7. 16.7, yeah, that sounds good. 16.7. And are we okay with the number of significant figures with that? We are, right? Because I've got 24.5, so that gives me 3. So my answer needs 3, and 16.7 is 3. And I guess that's it.